Okay, good morning and welcome to today's seminar. And today we have Professor Gregory Beroza from Stanford University, and I'm delighted to have his in our seminars. This is one of the last seminars that Annals of Geophysics organized to celebrate the 25th anniversary of NGV. And before the seminar, a brief biography will be presented by Elisa Tinti, our colleague from the University of Rome La Sapienza. And at the end of seminar, we have time for the discussion. Thank you for your participation, and please, Elisa.
Hi to everyone. It's a pleasure to introduce Professor Beroza, the Wayne Lowell Professor in the Department of Geophysics at Stanford University and one of the most influential seismologists of our time. His research has significantly advanced our understanding of earthquake processes, particularly in earthquake source physics, seismic tomography, the detection of small seismic events, and uncovering new insight into slow earthquake and tremor. In recent years, Professor Beroza has made understanding contribution to our application in machine learning seismology, developing innovative techniques to analyze vast amount of seismic data, detect hidden earthquake signals, relocate events, and improve real-time monitoring. His work has been instrumental in advancing our ability to identify and characterize low earthquakes, non-volcanic tremor, anthropogenic events, and other seismic phenomena that were previously difficult to detect. Behind machine learning, Professor Beroza has played a key role in developing techniques for characterizing seismic events, providing crucial insight into earthquake nucleation and fault behavior, studying fluids and their potential triggering effect, and detecting the temporal evolution of groundwater recovery through seismic ambient field interferometry, as highlighted in one of the most recent papers in Science. At the time when seismic hazard assessment and earthquake early warning system are more critical than ever, we cannot think of the recent sequence that hit the Myanmar region and nearby town, causing significant damage up to 1,000 kilometers away. His research is of paramount importance in guiding the future of earthquake science. His contributions are not just academic. They have a real-world implication for hazard mitigation and public safety. He is a fellow of the American Geophysical Union and the Seismological Society of America, and his contributions have been widely recognized for their impact on earthquake science. He has also served for many years as co-director of statewide California Earthquake Center, a collaboration of more than 1,000 scientists from over 100 research institutions. Today, we have the privilege of hearing from Professor Beroza himself. Please join me in welcoming him. He shares his latest insight into seismic phase association and earthquake location with graph neural network. And at the end of presentation, there will be time for questions for both audience in the room and those join us remotely via YouTube. Online participants will find a Google form link on the YouTube page to submit their question to Greg. Please.
Thanks, Elisa, for that very generous introduction. And I guess I should say happy anniversary to INGV. It's a great honor to be asked to come and give a talk to this wonderful institution. And as the title says, I'm going to be talking about sort of technical things and seismological things, but it's, I think, relatively straightforward to map the sort of approaches that I'm using to other fields. I think there's a lot of opportunity there. So the figure on the right is something that is the result of Google Gemini. I asked it to create a figure that shows global earthquake monitoring with AI. And if you look at it closely, there's some seismogram-looking things, but if you look at the charts, it looks like a medical operating room or something. But this is the best. So it created several images. This was the most relevant one. Anyway, so AI is changing all that we do. So as Elisa mentioned, I've been working on using methods of AI for earthquake monitoring. And but there are many different ways in which it can be used. So in seismology, we're very fortunate in that we have lots of data, and in particular, we have lots of labeled data. So we have literally millions of examples of P waves and S waves that are labeled, that are quality controlled, and that is essential material, essential information for supervised machine learning. So all of this work owes a debt to the people who run seismic networks, the people who maintain data centers to distribute data, and to the seismic analysts who did the hard work to pick and quality control the data that's used in these machine learning models. So one of the models that has been used a lot is PhaseNet. It's designed to pick weak P and S wave arrivals. So we already know about the big earthquakes. This method is trying to find the small earthquakes by classifying wave arrivals. So we treat this as what's called a semantic segmentation problem, meaning we give a name to each point in the time series, or really we classify the probability that it's one of three things: P waves, S waves, or noise. So 3 component seismograms in, 3 components of probability classification, probability out, and that's what's shown at the bottom there. And we design it so that the probability peaks at the labeled wave arrival time. And this is Wei-Chang Zhu, who developed this when he was a grad student. And this approach works very well all around the world, including in Italy, where Yenjo Tan and others in this room were involved in a study of the 2016-2017 sequence in the Central Apennines. What's shown in black are the additional events, about a little more than a factor of 10 more earthquakes than were in the standard catalog. And those were developed with the benefit of about 30 million P-pics and about 30 million S-pics. So that's a new capability in seismology, to be able to pick so many S waves. P waves are relatively easy. They're the first arrival. S waves are more difficult, but machine learning models can pick S waves very effectively, just as effectively as P waves. And so what this, skipping back and forth one. All right, well, we'll go straight to this. So this is the largest induced earthquake so far in central Oklahoma. This is the USGS comprehensive catalog, known as COMCAT. It's color-coded by time. You can see the distance scale there is about 3 kilometers. The map is supposed to show you where it is, but you probably don't know where Oklahoma is. It's sort of in the middle of the US, and each one of those dots represents an earthquake. So using the same data, we apply our machine learning model, PhaseNet, to pick seismic phases. We relocate the earthquakes, and we transform the view of the seismicity into this. So there's obviously much more information in this catalog. What previously was sort of a fuzzy trend or pair of trends, we now see that trend is apparent at 2 or 3 different spatial scales. So at every resolvable scale, we see this sort of conjugate faulting with about 120 degrees between the slipping planes. And in other parts of Oklahoma, we get similar, and Kansas, we get similar resolution. So this is, should I click on this, or what should I? I'm not sure how to get rid of that thing. This is the Woodward sequence. The largest is magnitude 3.8. There are 89 magnitude 3 plus earthquakes on this image. Thank you. But none as large as magnitude 4. And it's, again, color-coded by time. It shows bilateral and then down-dip migration over sort of a 10-year time period. Here's the Fairview sequence. This had a magnitude 5.1 earthquake in it. The distance scale is about 5 kilometers. You can see this really beautiful, in the lower left, this horsetail splay expressed in the precisely located seismicity. Again, we see the conjugate trends. Here, this is another part of Oklahoma, central Oklahoma. We see only one trend is really dominant. And I should emphasize that these faults were not previously mapped. So the mapped faults are in the overlying sediments or sedimentary rocks. These are in the basement. And the reason we know that they're there is because of the earthquake activity that's being triggered by fluid injection. So we can use these machine learning models to uncover new things, and we can also use them for motivating a process-based understanding or physics-based understanding of what's going on. We've now switched to Canada. This is the Marzo Lake, again, induced earthquake sequence. This shows the figure on the left shows our catalog in red versus the Alberta Geological Survey catalog in gray. Here we have almost 100 times increase in the number of earthquakes that are cataloged. So there's much more that it's possible to see. This is a map view of those earthquakes. They're related to fluid injection. We can see the sort of characteristic diffusion of seismicity with time, with very high diffusivities, as has been observed for induced earthquakes elsewhere. And if you look closely, you can see that some of the trends, some of these early trends, actually go in the other direction. So even though the overall propagation is away from the injecting well and shows diffusion, there are trends within it that are reversed and may be helpful for understanding the mechanism. Important for policy is that most of the large events, this is Ryan Schultz who did this work when he was in grad school, most of the large events are here in the Precambrian basement rather than where the injection is happening. The injector wells are shown up here. So that can help to, in that sort of understanding, which we didn't have before, can help to inform policy decisions and traffic light protocols, things like that, for avoiding earthquakes that we don't want to induce. Okay, so this is just work that my group has been involved in. So there's 15 different places around the world, including a couple of places in Italy. So the Apennines, also Campo Flegrei more recently. And it represents obviously diverse tectonic environments, including volcanic environments, extensional, compressional, subduction zones, continental strike slip. And we're using the same sort of approaches. So using PhaseNet mostly without retraining. That is mostly just the California model. Does very well at measuring P waves and S waves. So that's great. But all these studies are carried out with waves that don't propagate very far. That is what we call in seismology local wave propagation, or propagation through the crust. So the stations that we're using to monitor these earthquakes are located within about 150 kilometers or less. And so that has implications for the universality of the model. For most of the world, that's not going to work. And it won't work because we don't have enough seismic stations to do local earthquake monitoring. So what this figure shows, it's maybe a little bit hard to see, but the areas enclosed in green are the places where we can do local earthquake monitoring, or at least at one point we could do local earthquake monitoring. So for parts of the US, that's colored green because the transportable array passed through 10 years ago. But we don't have local earthquake monitoring in some of those places anymore. So this is kind of an optimistic picture. Anyway, the areas enclosed in green, we can do local earthquake monitoring. If we consider the distance range out to about 20 or 30 degrees, then we can do regional earthquake monitoring. So these are waves that propagate through the upper mantle. Those areas are outlined in pink or purple, not sure what color it is. Anyway, that includes much more of the world. But then there's some areas, like most of the oceans, parts of Africa, northern Russia, where we don't even have regional monitoring. So we're relying on to do earthquake monitoring in those locations. We rely on teleseismic wave propagation, meaning waves with turning points in the lower mantle. And so our PhaseNet and local earthquake monitoring isn't going to work in those locations. So I'd argue that this shows that we can do machine learning models and improved catalogs in any environment. But if we want to do the whole world, we've got to, if we want to do it everywhere, we've got to meet some outstanding challenges. The first of those challenges is measuring regional seismic phases. So this is an earthquake in California. That's Leonardo Aguilar, who did the work for this. A local earthquake seismogram in California, you can see a characteristic sharp crustal P and S followed by an S wave. That's the sort of data that PhaseNet was trained on. But at the same earthquake at larger distances, this is an earthquake in Northern California recorded at 500 kilometers distance, the waves propagate through the upper mantle. They're much more emergent, and you get a crustal arrival as well that is not the first arrival. So in order to pick phases for this kind of data, we need, and by doing so, do regional earthquake monitoring, we need to retrain our models. Now, SeisBench provides an environment for doing this. This is from Willem et al. 2022. We have, and what's shown on the right is the distribution with distance of labeled data within those data sets. Most of them are concentrated at local distances. The instance data set for Italy is an exception, but they generally lack, at least in global coverage, intermediate or regional distance waveforms. So we set about to change that by creating a data set for regional waveforms with labels called CREW. We have PG and PN labeled, and then generically P and S. This is the distance distribution. It goes out to 20 degrees, has millions of examples of these labeled waveforms. Leonardo's from Colombia, and we're interested in creating a catalog for that country. It's a big country. Shown in blue are the National Seismic Network stations. Shown in green and shown in yellow are, for California and Japan, what the seismic network footprint would look like put on Colombia. So you can see how dense it is in California and Japan. This is HiNet plus FNet. And we really, even in a place like Colombia, we need this regional monitoring capability. Okay, so we trained basically a version of PhaseNet to work for regional phases. So what's shown up here are the 3-component seismogram. Shown here are for this model, the first arriving P and first arriving S wave. And these are and a representation of the features that this UNet architecture learns. So it goes through a bottleneck to learn features that are both compact and expressive in terms of the labels that we want to reproduce. That's the training. We have an additional 5 layers in this model compared to PhaseNet, because the receptive field, the length of the seismogram that we use is 5 minutes rather than 30 seconds, because the waves are much more spread out. So we have more spread out waves, but we want this part, the encoding here, to be just as expressive of the features in the waveform as for HiNet. So we had to add extra layers to do that. Our data are almost 2.5 million labeled arrivals, so plenty of data to train a model like this. So I'll just go really quickly. The same kind of output shown with dashed lines are the label that we're trying to predict. This is from data that was held out of the training. Shown with the solid lines are the output of the model. So here it does quite well at picking first arriving P, first arriving S, whether it's PG or PN. Here's another example. There's a little bump here. See, the data in this case is very noisy, but it still does a fine job of picking out the higher frequency P and S wave arrivals. Whoops. Here, one of the things we do is augment with multiple wave arrivals. Here it does a really nice job of picking up multiple arrivals from multiple earthquakes and so on and so forth. This one, I think, this one worked. I think I have an example where it didn't. Yeah, so this one, it worked in picking PN, but for this event, but for SN for that event is in the coda of this other event, and it failed to pick that. So it's of course not perfect, but it does pretty well at picking the first arriving PNS wave from multiple events. We have a much smaller data set for which we have all 4 of those phases available, but we trained a model to pick PN, PG, SN, and SG. It works best where those phases are clearest and well separated, 3 to 7 degrees epicentral distance. This is just examples of where data that was not used in the training, how we can pick all of those phases. So anyway, so that sort of checks one box. We've got the regional wave measurement technique, and the teleseismic wave measurement we haven't worked on, but I expect it should be straightforward. So go on to the second challenge. The second challenge is what's called phase association. And to be able to do phase association, which is connecting the earthquake or the phases with the earthquake or seismic source that caused them, that's surprisingly difficult to do. And my attempt to express that is with this pond where there are raindrops falling. We have waves propagating across the pond. We, of course, in seismology don't get to see the whole surface. We just have very sparsely and discretely sampled parts of this field. There are waves coming from different directions, from different sources. They're little drops, they're big drops, small and large earthquakes. All of these pose challenges for phase association. So it's discretely sampled. The number of earthquakes we don't know a priori. We have overlapping waveforms, particularly at interesting times like during swarms or during aftershock sequences. Small earthquakes are recorded over only a very small part of the network, and so you have to ignore, in order to detect small earthquakes, which is what we want to do, you have to learn to ignore almost all of the data, but still register a detection. The network changes with time. It's not Euclidean. It's not evenly spaced. It's very irregular. You got background noise, seasonally, different times, so forth. We have false arrivals because of that noise that aren't really, phases that shouldn't be associated. And it's just a difficult task. So as the title promised, I'm going to talk about using graph neural networks. And I wanted to point out that, so I went to see where graph neural networks came from. They came from Italy. So this is the first paper on graph neural networks, University of Siena, people in the engineering, information engineering department. And this is the first figure from their papers showing a neural network representing somehow a house that's very irregularly sampled. So they didn't have seismology in mind, maybe engineering, but it's amazing how much is in this paper, and kind of humbling to realize that it's 20 years old. So this idea has been around, of using graph neural networks, has been around for a very long time. But like a lot of which is true of a lot of neural networks and machine learning, but it's only in the last 5 to 10 to maybe 15 years that it's really gotten traction, and these ideas have really been begun to realize their full potential. So why should we use graph neural networks for phase association? So things like PhaseNet use convolutional neural networks, and those are great for Euclidean data. And by that I mean data that's evenly spaced, like an evenly sampled time series. In an evenly sampled time series, convolution in one part of the time series means the same thing as it does in the other part of the time series. Same thing goes for images. You can learn features using CNNs, as they're called, but they only are learned reliably if the sampling of that feature, the pixels, say, in an image, are evenly spaced. Recurrent neural networks are used for cases where the sequencing of signals or things within the image matter, and that's what you want to learn. So, for example, the P wave be coming before the S wave, that's something we want the neural network to do, so we might choose a recurrent neural network to learn that property of seismograms. Graph neural networks are designed to work with non-Euclidean data, so they're designed to overcome this shortcoming of if you want to call it that, of not having evenly sampled data, not having a natural ordering of things, just as you would from a seismic network. It depends on where the earthquake is, how the move out will track across the network. And so you can't, with a regular neural network, it's very difficult to train a model to learn what it needs to learn to do association. So it needs to learn move out or wave propagation and amplitude. We use amplitudes. It needs to learn that P waves come before S waves, that small earthquakes are only located are only detected by a small part of the network. All those kind of things go into it, and graph neural networks provide an effective way to do that. So this is Ian McBrearty. He's the grad student, soon to graduate, who's been working on this problem. And so it goes something like this. So shown in the figure to his upper right is a station graph for California. So each one of those dots represents a station, and then the lines, which you probably can't see, that connect stations represent an edge in the graph. And then the one in orange is a potential source graph. So those are potential source locations. We take the Cartesian product or outer product, all combinations of those two, and that's the graph that we interpret the data through. That is, we do the deep learning with. Our other input is PIC data. So this is synthetic data. There are 2 earthquakes in here, and then many, 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 many bad PICs. And the reason we do that is we want to be detecting at a low detection threshold, and we want our associator to ignore bad PICs. So that's the input to the GNN. The output is sort of a probability distribution or a heat map of the location and the origin time of the earthquake. That's the part we're most interested in, but also which of these phases are associated, P waves and S waves. And kinematically, there are probably many of these other false PICs that would line up in a back projection scheme, but the genie, as we call it, has learned not to associate those. So that's what we want out of an association model. We want a sort of quality control on the data. So it turns out we have to use fairly sparse networks in order for this to be computationally tractable. There's a station graph. There's this is just the station graph. But what this shows is that the graph, once you do these convolutions, you connect different parts of the graph with each other. So as long as through a few convolutions, you can connect the different parts of the information on different parts of the graph, you can learn by doing that the move out and the distance decay, all that good stuff that makes for effective phase association without doing the back projection that's usually done, reverse time, explicitly. So this just shows examples, again, for Northern California of, and this is for real data, this is all the PICs it has to work with. It's smart enough to just associate some of those PICs, and it's localized spatially. Magnitude 2, this has a larger footprint across California. It's ignoring all these phases out here that could potentially line up. And magnitude 3, it does well at detecting over a very large part of the network. So those are all properties that we want an associator to have. We also want it to not associate bad PICs. So we did an experiment with the first week of the Kahraman-Marash aftershock sequence using one of our other associators, which uses a Gaussian mixture model, versus the graph neural network-based associator. This found more events, but you can see that the locations form a cloud, so we think it's making bad associations, which is not surprising, right? Because all along, there are earthquakes happening in all along these fault zones that ruptured in the earthquake in the main shock, and it's having to untangle all those arrivals. Genie, because this is an unsupervised method. Genie is supervised. That means it's trained on huge amounts of data. It has learned how to do that effectively, and we can demonstrate that by adding bad data to the data we have, and look at this curve here. This is with 10% of the picks added being just random. Gini will find a couple of hundred events, Gamma, whereas Gini, the graph neural network-based model, suppresses these spurious or called phantom events more effectively. Okay, so in order to do this globally, we have to, of course, go to spherical geometry. We have even stricter computational requirements because we have to cover the Earth with a source graph and a station graph. So we need very sparse graphs, but those graphs need to connect over scales once we do convolution. So far we've been using sort of random sparse graphs, which work pretty well, actually. But there are formal ways of doing this with something called expander graphs that allow you to connect over scales in order to learn the same kind of things, move out and amplitude decay. So I'll just show you very quickly a global application. These are the stations. There's about 1,400 stations that are reporting to the National Earthquake Information Center of the US GS. That's our station map. We create a station graph by having edges to the 10 nearest neighbors. We need a source graph that covers the world. This graph has a name, but I forget the name. So some mathematician came up with this graph that approximately covers the Earth's surface at equal area. So we include edges for the 15 nearest neighbors in this source graph. But everything else is essentially the same. So we take the outer product of these two. It creates a gigantic graph. We have picks that go into the graph neural network, and we have a source prediction. So space, time, and not shown here, but which of the phases are associated. So this is sort of the typical thing that's shown for machine learning models, that the loss function as a function of the update step. This is the label we're trying to reproduce. This is the prediction. So it works at this larger scale. We recovered 95%. This is for a 2-month time period. We recovered 95% of the USGS cataloged events around the world. This is not really an fair comparison because Comcat uses data that we don't have in this model. And I should note that these are just, ordinary picks. We haven't taken the step to do machine learning for phase pick globally, which would increase the number of, the amount of data by probably a factor of 10 or so. But in just about everywhere, between 90 and 100% of the earthquakes are recovered. This is Alaska, 92%, South America, 98%, Europe into Central Asia, 98%. So it doesn't seem to be biased. It's working globally. And it's also detecting new events. So those are events we already knew about. It's detecting many new events. So this is for the eastern US. The comprehensive catalog reports 17 events greater than magnitude 0 during a 10-day time period. We apply Gini to the same data set, and we get 739 events. That's typically how many the USGS lists for the year. Again, this is maybe not a completely fair comparison because they at least try to filter out some of the quarry events. Many of these events are happening during the day and not during the night. Good example is this cluster in northern Minnesota. The events are shown here in a histogram by time of day, and you can see they cluster during working hours, and there's known to be a big iron mine in that location. So that's what we're detecting. So that's the second challenge, doing this globally. The third and final challenge is how do we locate these massive populations of earthquakes? This is from a really nice paper by Waldhauser and Schaff, 2008, where they made a double difference catalog for Northern California. 311,000 earthquakes, 7 million p-picks went into this. The number of picks you can make scale, it's n times n minus 1 over 2, so potentially millions and millions of picks. They took only a small subset of that. Nevertheless, they had something like 3 billion differential times to work with. That's their data dimension. So they divide, in order to run HypoDD on this, they divided this into about 500 boxes and located within each of those boxes, just to make it computationally feasible. Well, we're working on developing a machine learning catalog for 24 years of data. That's 280 terabytes of data that's been processed. And we don't get millions of picks, we get billions of picks. So we get something like over 2.2 billion picks. Those are direct picks. The differential, you know, if we did every differential pick possible, we would have on the order of 10 to the 18th picks. That doesn't make sense and wouldn't be feasible to work with under any circumstance. But the point is that we're orders of magnitude richer in measurements, and so we need a new way to do the earthquake location. We don't want to have 50,000 boxes or whatever it would take to do that. Here's our initial association results. We get about 8 million earthquakes. So, and we're probably only going to save a subset of those that are we can locate precisely, but very much larger earthquakes. So how could we locate these earthquakes? Well, again, not surprisingly, we're going to use neural networks. Here's our station graph as before. Here's our source graph. And we're going to take the Cartesian product and we're going to train a neural network model. But now what we're going to train it to do through minimizing the double difference residual is to update the source graph. Right, so this is sort of like an autoencoder in that the input and the output are the same. But you may notice that we're not doing the entire source graph. That would be, in the case of California, that would be 8 million nodes and who knows how many edges. We're subsampling it, and we're going to. And the idea is that we create these perturbations of the source graph, which are the earthquake relocations. Now we have to do that over and over and over again so that we sample all of the sources, but we can do that. That's the way machine learning models are trained. We do this batching of what's called batching of the source graph, and that limits the memory requirements and allows us to overcome the memory limitations of doing a joint relocation of 8 million earthquakes, which is what we're aiming to do. We minimize the L1 norm, which is different than standard HypoDD, and we use something called the memory state to accelerate convergence. So the memory state just means that these sources will be sampled multiple times, and rather than starting the second time you sample it, rather than starting from no perturbation, you give some weight to the perturbation that's already had. It's sort of the obvious thing to do. It's got a name, so I thought I'd put it up there. But it makes it converge much more quickly. And we add it to get accurate locations, not just precise relative locations. We add an absolute loss term to the absolute residual term to the loss function. Station corrections we add. And then if we want to, we can calibrate to an existing catalog with this capability. There's a lot of opportunity for doing different things, creative things, different graph strategies you could use. Two are shown here, nearest neighbors versus a neighborhood map. These are instances of source graphs. And then the Cartesian product on which we do the learning is the outer product of these two. So how does it work? Well, this is from Yifan Yu's paper, at least published online last year. It's not in print yet. But what's shown here, this is on the left, 2 columns are accuracy, the right 2 columns are precision, and the bottom line is graph DD, graph double difference, what I'm showing here. And it's comparable in performance to other advanced methods. And you can see that if you apply it to the data from the creeping section of the San Andreas Fault. It does what HypoDD always does. It sort of compresses the seismicity onto the features that we know are active. Works the same sort of thing for the early aftershocks of the earthquake in Turkey. We created a synthetic million event catalog where we knew the ground truth for California, and we're able to do a joint relocation of a million earthquakes. And then for real earthquake data, this is from from northern Chile, about 750,000 earthquakes in the subduction zone and the overlying crust. The middle panel shows the graph double difference locations in map view and in side view, and compared with a smaller set of Sippel et al.'s hypo-DD relocations, we see we do quite well at reproducing things like that we know are there, like the double seismic zone. So in conclusion, I'll say that GNNs are an effective tool for phase association and location, and that they are effective across scales. I didn't show it for the reservoir scale, but we and others have done it at the reservoir scale, and it works quite well all the way to the scale of the entire planet. As usually done, phase picking, association, location, and then an output of a catalog are usually done one step at a time, with information being thresholded at each step. But all of these are coupled, right? If you have phase picks, that allows you to do association. Once you've done association, you might consider going back and looking for other picks. And likewise, location and association. If you misassociate a phase, you'll get a bad location. So there really ought to be feedback between these processes rather than putting them all in a line. It can be a computational challenge, but I think something like that, some sort of all-at-once approach that exploits that coupling, that information context, is ultimately what will give us the best catalogs. So I'll stop there, and thanks again, and take any questions. There's a big microphone on that. I don't know if it works.
Thanks, Greg. Very interesting presentation. I think it's starting a big revolution in how we see and how we look at seismicity. And I have many. I have a principal question, but I also want to say that we are very interested in collaborating in improving the regional training. We have some experiments at regional scale, like Adria Ray and with many seismic stations on the Balkans and the Naric area all over the Adria plate. So we are really interested in improving the performance at regional scale. So I think that maybe we can remain in touch for this.
I would be absolutely delighted to do that. I've never worked at regional distances because it's so complicated. So I don't have a really strong idea of what to do. So if you have ideas, I'd love to hear them.
Yeah, and a scientific question is, even when you relocate very accurately with double different methods, the seismicity of so large data set, you obviously improve your imaging of structure and faults, but you still have some clouds seismicities, or maybe the seismicity is not clustered on a specific structure. What do you think about this seismicity? Is real?
Yeah, it sort of depends. So some of that, the seismicity in those clouds is no doubt real. I mean, it's unrealistic to expect things to be razor thin. We see in geologic expression of fault zone damage zones that can be hundreds of meters wide. So you expect, and faults are really fault systems. So I wouldn't expect it to be very narrow necessarily. On the other hand, when we make a mistake, like we misassociate a phase, or we call it a S wave when it's really a P wave, that will send it won't completely destroy the location, but it'll make a cloud. And so what we're trying to do is to come up with better ways of figuring out when we've made a mistake, so that what is left is reliable and can be interpreted. But that's an issue. There's a trade-off, and it's not always clear where it is.
Hi, Greg. Thank you. Probably you already know my question is about the magnitude. I mean, you are. I think that I'm really impressed about the quality that you have to detect earthquakes that were undetected before, and also about the location. but do you have some idea, or is there something that people is doing to improve also our capability to assign reliable magnitudes?
Yeah, so that's a good question, and it doesn't surprise me that you asked it either. So we developed a machine learning model for estimating magnitude from a single station, and it worked quite well, given that it was a single station. And we worked very hard to preserve amplitudes in that, in making that model, because that's what magnitudes are based on, usually. But I don't think that's necessary. I mean, I think it would be possible to estimate magnitudes more reliably than we do now by using, even without the amplitude, the frequency content, the relative to the noise, and how it's expressed over a network. In the association process in Gini, there is an amplitude decay in there. So it effectively has a magnitude built in. And so something like that, embedding it in within this larger processing scheme to output a magnitude as well that accounts for local wave propagation characteristics, I think would be very promising. I have to admit, we haven't worked very hard on that, just well enough to do the association. But it should be possible.
Greg, it is more than a question, it's a comment regarding also what Claudio was mentioning and related to these coupling issues, let's say. So, I mean, when creating this catalog, so pushed in numbers and magnitude as well, so how do you consider the use of cross-correlation? I mean, is it something that is advisable, let's say, or is fundamental? Because I have the feeling that this is really the only way so far that we have, despite these new approaches, you know, to correct and filter in number what we got out from this huge association or binding problem.
Yeah, it's a great question. So I think cross-correlation-based arrival times are absolutely critical to getting a clear picture. We did that for the Turkey example, but not for the Northern California examples. We just took differential times to form the residual. But if we use the cross-correlation based differential time, those images would sharpen up considerably. And very often that's what, it's this geometry of the fault that we want to get, and the exact relationship of one earthquake to another, so we can see if stress triggering is, or a seismic slip or something else is necessary to understand them. So I think the cross-correlation, even though I didn't show much of it or emphasize it, I think it's absolutely critical to getting these really high resolution images. The ones I showed for Oklahoma and Kansas at the beginning in Canada, those are all based on cross-correlation based arrival times.
Thank you, Greg, for this seminar. A couple of questions. We have a lot of data, as you say, but we have a lot of bias we are going to bring inside our knowledge. For example, with FaceNet, we say that the error or the picking is symmetrical, is a Gaussian, because from nearly 80 years, 80 years ago, we were not able to deal with an error different than Gaussian. Today, with nonlinear algorithm, we can do it, but unfortunately, all our database say that we have a Gaussian error, which is not. So obviously, our AI is going to say, it's Gaussian error, because you say to me that it's Gaussian error. This is the first question.
Yeah. So I have trouble with these multi-part questions. So let me answer the first question. So the weird thing is it doesn't matter very much what you, so the label is a Gaussian that we truncate for FaceNet. It doesn't really matter very much. You can train it with a boxcar. The regional network picker we trained with a triangle, but you don't get a triangle back. You get something different. And it's that, and the width of that distribution, represents the classification probability, the uncertainty in that, rather than the uncertainty in the arrival time. and that's what you really want. And that's probably, and that's not Gaussian distributed. It's probably Laplace, a double exponential kind of distribution. But there's work to be done in characterizing the true arrival time error.
The second part.
Thanks.
And I see your graphs are huge, especially the source graph, because obviously, and there is not problem of repetition. After that, when you have millions or billions of nodes in your graph, in a way, it is like you see you have a very huge ghost script, and it's at a point, there is so many points, it's better to have a raster image of the problem more than a graph, because it's help you to deal with the number of your data, and it's going to sample naturally the amount of information you have per areas, because if you have so many stations, maybe the weight of this zone is going to be preponderant with respect to other information, which maybe, because there are fewer, are much more important. I don't know if it's clear.
Yeah, so I think I understand the question, and I'll answer what I think I understand you to be asking. That is, couldn't you just take a grid and do that? And that's what reverse time methods tend to do. Even though it didn't look like it the way it was plotted, 5,000 source nodes spread across the Earth is pretty sparse, and our the neural network effectively does an interpolation between them to make its prediction. And even so, we have to use a pretty sparse graph, not too many edges that connect the nodes for either the source or the station graph. If we were to go fully raster, fully pixelated grid search kind of thing, that would be more expensive, a lot more memory intensive. I don't think it's the way to go, at least not yet, but who knows? Maybe someday it could be.
Very nice seminar, thank you. My question, I'm not sure it's relevant to what you shown, but I kind of connect to what Werner was saying earlier. He was talking about magnitude. And I have, my problem in general is that look at a waveform and decide if it's good or not. Good or not meaning no holes, no spikes, no local noises, no missing data, no double earthquake in a certain window. Mm-hmm. And I can do that in, just looking at waveform. I in the blink of an eye, I know it's good or it's not good, and I can pick it or just, can we do anything like you did, or can the technique that you are using be used for that kind of sampling, that kind of picking data?
Yeah, that's a really good question. So we use machine learning for quality control all the time. That is, we don't necessarily explicitly look to get rid of spikes, although sometimes we do. So we did some work, we're doing some work in Kepa-Flegrei. There were a couple of stations that had these persistent noise spikes unrelated to earthquakes. We were getting many, nevertheless PhaseNet was picking arrivals. So we retrained the model. We said, here's a bunch of noise, and it was data from that station that had basically spikes in it. And it learned not to pick that. So what you're describing in terms of magnitude, you can augment the data. So take reliable data, put a spike in it, and you can either train the model to reject that data because it's got a spike, or you could train it to ignore the spike and calculate the magnitude anyway, much like you would do if you were doing it by hand. So it should be possible. And, it's probably a really good idea to do that.
Yeah. For example, I have a data set of 500,000 waveforms that I look one by one. And I decide which one is good, which is not good, which was not good. And I was thinking to find out a way to train a code to do a supervised, machine learning
Yeah.
thing.
So there's something called semi-supervised learning where there's a person in the loop. So I'll give you an example for PhaseNet. So PhaseNet, we were applying it to Tonga, Fiji, OBS data, different kinds of noise. And so we retrained it to work on a few, really just a few thousand examples of PNS pics from earthquakes from that OBS data. And then we ran it on the year of continuous data, did the association, and the association said that some of those were real pics, some of them were not. And so we used that, the associator as sort of the person in the loop, to either preserve those new pics or to get rid of them. And then we retrained on the new pics. So it's a recursive thing. And what you're describing, I think it could be, without having to look at 500,000 waveforms, you could look at 2,000 waveforms or 1,000, train a model, and then however you need to, depending on how well it works, sort of bootstrap your way up with the computer helping you to sort them into good versus bad data. So that would be a semi-supervised approach that would be, has advantages of both.
Thanks for the seminar. You talk about a computational expensive about graph neural network. Can you quantify a little bit that part?
Yeah, so I can't really quantify it except but the important thing to understand about them is that these networks are very expensive to train. So with Genie, I think we used at least billions, if not tens of billions of examples, synthetic examples to train on. So that takes a long time and takes a lot of, usually we try to use GPU computers for that. But once it's trained, then you can apply it quickly. So for PhaseNet, you can do PhaseNet in real time for a network on the cloud, right, with like 20 processors. So yeah, there's sort of an investment up front that's a lot of computing. That's what computers are for, right? And then you can, once you've got that, you can run things quickly. Yeah, great question.
Thank you very much for your very interesting seminars. When we look at seismicity on volcanoes, especially when the dynamic of the volcanoes begin to start very important, we recorded different type of earthquakes, not only volcanotectonics, but also long period and very long period and ultra long periods and tremors. Do you think that an approach like PhaseNet may be used in order to locate also this kind of seismicity, since this kind of seismicity has the track of the moving of the magma flow toward to the surface, and the practical of the observatories, in particular the volcanic observatory, will be very useful to have the possibility to locate in quasi real time such a seismicity.
Yeah, so that's an important question. I'm pretty new to studying volcanoes, but we've been using our methods we've been trying them on Etna, on Campo Flegrei, recently on Santorini, and also in Mayotte. And using PhaseNet, we've been able to detect at least long period earthquakes. And this is an experience from Mayotte in the southern Indian Ocean. PhaseNet was making the pics, but they were using earthworm to form the events, to do the association, and the earthworm associator won't create an event based on S-wave pics. And so they were losing all these pics. And so there are things like that you have to account for. So I think at least for long period earthquakes, it would work. But there are other events, and for characterizing things like tremor, I'm not sure what it would do. It would be interesting to with something like tremor to just take, or well, there's all sorts of things you could do, but you could imagine taking, instead of making discrete picks, you could take the classification probability output continuously and look for changes. I mean, there are all sorts of things you could do, and I'm not sure what makes sense, but I think you would have to, in order to understand the spectrum of deformation in volcanoes, which is very rich, you'd have to do other things too. But you know, you could use the similar kinds of approaches. Yeah, great question.
Thank you, Greg, for your seminar. So I have a question about the use of the graph neural network in the association, because as you mentioned, they somehow learn out the phases, the arrival times, move out through the stations. But when moving to a regional approach, when building the graph for the station, beneath the graph of the station, you have some very different velocity models. So how far, to what extent you can also mix the information worldwide, and you have different sources from different depths, crustal seismicity, and
These are good challenges that I didn't address in my talk, and I haven't addressed in my research ever. So we are relying on at this point, relying on a collaboration with the NEIC in Golden, Colorado, and they've been navigating those issues, well, forever, you know, as long as they've been running. But there will be challenges in the association, because you have to predict the arrival time. For the local stuff in like California, we're actually using a iconal solver, machine learning based iconal solver to do the prediction. That wouldn't work at regional distances. You have to do something different. But there are people who are working on model predictions for phases that in 3D structure that could be used for that purpose, including the depth. But there's clearly a lot of work to do before going global. Thanks, Francesca.
Okay. There is a question online, but first of all, I have a question related to this one. And what do you think about the possibility to understand something about the stress on the fault? Thinking about that if you train in a region and you are able to detect events, associate and locate and so on, for many years, maybe in a region that there are cycles so frequently, 1,000 here, is it possible for you to detect, understand something about potential evolution of the fault on that region if the performance is reducing or something like that?
Yeah, and so it depends on the sort of time scale. We have been, I didn't show any of it here, but for some sequences in Oklahoma, Kansas that are induced, we have been tracking the stress evolution on the fault during a sequence to see how the stress leads up to the next earthquake. And so if in a Coulomb sort of model, you would expect the stress to be increased where the next earthquake occurs. If something like a seismic slip or continuing weakening is some other process is going on, then you wouldn't. And what we find is a mixture of the two. So that suggests that it's not just Coulomb stress triggering, but something else that's going on. Migration of fluids, a seismic slip, partial stress drop, all of those are candidates. But it's really, to develop a physics-based models base using this kind of information, I think is a promising direction.
Promising and challenging.
Yeah, of course.
Okay, a question online by Guido Maria Dinolfi. How are incorrect peaks or uncertainties in peaks handled in your machine learning method? How do these affect the final result? Additionally, what strategies are implemented to mitigate their impact on model performance? Thank you.
Yeah, so it's thanks for the question. It's difficult to give a simple answer to that. I can cite an example or examples from both Campo Flegrei and Santorini, where we had picks that were misassociated that led to bad locations that were deeper than they should have been. And of course, with volcanoes, you're very concerned about the depth of seismicity. So in that case, we were just suspicious of those events, and so we went and looked at them, and sure enough, the P wave was labeled as an S wave or whatever it was. But we really need a more scalable and general approach to finding those sort of bad picks. We have to do kind of forensics on the catalog and the things that go into the catalog to do that. And so we published a paper last year where we urged people to publish not just the catalog, but also the picks, so that one could compare different association methods and techniques for finding that kind of problem in the data. But it's an outstanding problem, and it obviously needs a lot of work.
I have another general question, is it possible? For people that want to use this catalog from machine learning, do you have any suggestion? Because maybe people can use it to do a secondary study on machine learning. So sometimes people say that 2 steps in the same architecture or method can be dangerous. Do you have any suggestion on that, or?
Yeah, well, it's a difficult question, because I mean, it used to be that there was like one catalog, and it was chiseled in stone. But the landscape's completely different now. Everyone's making a machine learning catalog. They're taking FaceNet and they're retraining it for their environment, and all I can say is that in this new landscape, catalogs are going to need metadata that describe what went into them. Ideally, they'll come with that would include the phase picks, both associated and unassociated, that went into them, and maybe, I mean, it's daunting to think, but maybe even the waveforms that went into them in some cases, so that a third party can go back and see what's in the catalog that shouldn't be there, what's missing from the catalog, that kind of thing.
Last question.
Yeah.
You present a very beautiful tool for the cure of we're not sure that the picking is correct, and how we are going to bind it with other station. So my question is about the cause of that. Do you think that in the future we have to change the way we are doing the monitoring, in the sense when you look at fiber data like DAS, we maybe have less beautiful data when you look at trace or channel, but the fact that you have your spatial continuity make you sure that you have exactly this peak is and FaceNet DAS is working beautifully, I must say. And in a way, perhaps the way we are doing the monitoring of earthquake with only one station, without any continuous, spatial continuous information, is wrong in a way. Because also we believe that we know exactly the amplitude, the coupling of our sensor with the ground, the response of our instruments, but we are not enough humble about or not knowing this information. What is your view of the future of the monitoring on this argument?
Yeah, so DAS will be an important part of the future of monitoring. It's as you say, it's very densely sampled. You get an unaliased wave field, which we're not used to working with, at least in earthquake seismology. The data volumes are tremendous, terabyte or more per cable per day. So we can't move that much data around very easily. But I think it's inevitable that things like that will be used for earthquake monitoring. If you go to any earthquake monitoring center, they won't have the seismograms in isolation. They will have many different seismograms, and it's that waveform context, even though it's aliased, that continuity in the wave field that gives network analysts the confidence that the pick is real. All this FaceNet stuff currently doesn't account for that, and so that's an obvious way to improve it. And anyway, I think that's the way we're going towards sort of a richer, deeper catalog with denser data, including DOS, that somehow all has to be synthesized into a consistent product that can form the basis for other studies.
Any other questions? If not, we can thanks Greg for this wonderful talk. Okay. Some info. The branch will be in the second floor, so you are invited to come. And Greg will stay here this afternoon, so we'll have scheduled some appointment. But if there are someone really interested to speak with Greg, you can refer to me or Paola to schedule also you in the meeting. The meeting will be in the Sala Multimediale. Okay. Thanks to everybody.
Thanks.